Today we are going to talk about surface integrals, which are cumulative totals of the output of a function over a surface. And we're going to talk today about how to define and calculate the surface integral of a multivariable function by using double integration. So let's get started. Now, as an informal definition, we've got our function here, f of x, y, z, a function of three variables, and we've got some surface S. And for the surface integral, you will see it denoted in the following way. You have a double integration symbol on the left to indicate the two-dimensional nature of the surface, and as a subscript, you will see a reference to the surface S over which you're integrating. You have, as usual, the function that you're integrating here between the integration symbol and the closing statement, which is ds for surface. And this represents a cumulative total of the outputs over the surface S, and our usual example applies. If this function represented the density of an object, of a surface, then the surface integral will tell you the mass of that surface. So if you know the density at each point of your aluminum foil sheet, of your bed sheet, you can use a surface integral to calculate its total mass, for example. Alright, so to actually translate a surface integral into a form that we can calculate, let's see the steps that we can take in order to make that happen. And for our running example, we have here the surface integral of the function f of x, y, z equals y over the unit sphere z equals x plus y squared for the values of x between 0 and 1 and y between 0 and 2. And the first thing that you need to do when the time has come to calculate a surface integral is you need to find a parameterization for your surface. So our surface is given here. I don't know why I said unit sphere. This is not a unit sphere. This is just a surface. The surface z equals x plus y squared. Now remember from yesterday's material that when we had the graph of a function of two variables acting as our surface, there was a very cheap and easy parameterization that we went to most often, which was to say that we were just going to let the x value be represented by the parameter u, the y value be represented by the parameter v, and then the z value we could get by replacing x with u and y with v in the equation. Now, since x does represent u, to say that x varies between 0 and 1 is equivalent to saying that u should vary between 0 and 1. And to say that y should vary between 0 and 2 is equivalent to saying that v should vary between 0 and 2. And so this description is what we're calling in our notation the set D, the set of all inputs u and v which are allowed to go into the parameterization and which will correspond to points on our surface. Alright, so now that we've found a parameterization, the next thing that we need to do, and I've gone all the way to the next page so I have time, is we need to calculate a specific double integral. The double integral that we need to take is the double integral over the set D, the set of all possible points u and v. This is a double integral, so the integral will close with the symbol dA. A is for area. Alright, what we need to do is we need to take our function f, and instead of having the variable x, we need to replace that with the x from the parameterization. Instead of having the variable y, we need to replace that with the y from our parameterization, and likewise for z. Now this notation is pretty bulky, And so this is often referred to as f of r of uv for short. Take the parameterization, stick it into the function. That's what we're doing here. But that's not all. We're also going to have to multiply that by a quantity which we will call Ru cross Rv. Remembering that R here stands for the parameterization that we've decided to use. So let's see what this formula looks like and apply it to our example. And let's recall that our R, our parameterization, was u, v, and u plus v squared. Now when someone says R sub u, what they're asking you to do is to go through one by one and find the partial derivative with respect to u of all the components of v. Derivatives of vectors are always taken one component at a time. So let's do that. Let's take the derivative of u with respect to u, of v, and of u plus v squared. So now, taking that derivative leaves us with 1 in the first position, 0 in the second position, and 1 in the third position. We'll need to do the same thing with the other variable v, and find the partial derivative with respect to v of each of these components. Okay, so as a result, we get 0 in the first coordinate, we get 1 in the second, and then 2v in the third coordinate. Alright, now we're still building and constructing the ingredients for our integrand. The next thing that we're going to need to do is we're going to need to take the cross product of these two vectors that we've just found. So let's calculate Ru cross Rv. Alright, the components of Ru in order were 1, 0, 1, followed by the components of Rv, 0, 1, 2v. And so let's calculate this. 0 times 2v is 0 minus 1. And then 1 times 2v minus 0, but make it negative. And then 1 times 1 minus 0 is 1. So we have now obtained the cross product of Ru with Rv. But there's still more work to be done, because in the formula we have to deal with the magnitude of the cross product in our integrand. So our next move is to go ahead and find the magnitude of the cross product, which can be obtained by calculating the square root of each of the individual component functions squared. Minus 1 squared, negative 2v squared, plus 1 squared. And so we get the square root of what appears to be 2 plus 4v squared. Alright, so there's the magnitude of our cross product. And we have filled in one of the two blanks in our integrand here. The next thing that we need to do is we need to go and gather up our function f of x, y, z and replace all the y's, x's, and z's with their parameterizations. And the function that we had was simply f of x, y, z equals y, where y is v. So a function f, in terms of our parameterization, we took that y and we replaced it with v. So finally we've got our integrand. We're taking the double integral over the region D of the function with the parameterization plugged in times the cross product magnitude, 2 plus 4v squared. Of course, to actually calculate the value of this double integral, we have to translate it into an iterated integral. And this is the point where we remind ourselves that D was the set of all uv, so that u varied between 0 and 1, and v varied between 0 and 2. Varied between 0 and 2. So just a rectangle, very convenient. So let's set up those limits. V goes between 0 and 2. U goes between 0 and 1. Integrating v, the square root of 1 plus 2v squared, 2 plus 4v squared, excuse me. Okay, and then let's try and apply power rule correctly. So we would have 2 plus 4v squared to the power 3 halves times 2/3 from power rule. And then we're missing an eighth from the derivative of 4v squared. Okay, that should be right. Evaluated as v goes from 0 to 2. And then we still have our u integral. And if we clean that up ever so slightly, let's see. If v is equal to 2, we get 2 squared, 4. So 4 times 4 is 16, we get 18. So 1 over 12, 18 to the 3 halves. And if v is 0, we get 2 there. So minus 1/12, 2 to the 3 halves. Integrating that from 0 to 1. Now this is just a number and it doesn't have any u's in it. And so we can just multiply by the length of this interval from 0 to 1, and we get 1 over 12, 18, 3 halves, minus 1 over 12, 2 to the 3 halves. And that is the value of our surface integral. Now this is one of the simplest problems in terms of surface integrals on the face of the earth. And unfortunately, even then, you know, this is quite monstrous, isn't it? This stretches across, what, 3? Oh my goodness. This stretches across many, many pages. And so we will very quickly be moving towards some theorems that will make it a little bit easier to calculate these if we're lucky. Some theorems by the name of the divergence theorem and by the name of Stokes' theorem. But in order to get there, we need to first talk about surface integrals, not of multivariable functions, but of vector fields. And we'll be talking about that tomorrow.